Antarctica is a land of extremes. It is the coldest, driest, and windiest continent on Earth. In the depths of the southern winter, air temperatures regularly fall below -40 degrees Fahrenheit. Around the continent, the ocean freezes into an immense shield of sea ice that spreads outward for thousands of miles, nearly doubling Antarctica's apparent size. From above, it looks solid, continuous, sealed. And yet, in the mid-1970s, satellites looking down at the Weddell Sea saw something deeply unsettling. Hundreds of miles from the nearest coastline, in the middle of the winter pack ice, there was open water. Not a thin crack, not a narrow lead, but a vast, persistent opening, a region of exposed ocean surrounded by solid ice on all sides. At its maximum extent, this opening covered hundreds of thousands of square miles, roughly the size of New Zealand. Even more astonishing, it remained open through 3 consecutive Antarctic winters, from 1974 to 1976. In a place where the ocean should freeze shut rapidly, the ice simply did not close. Then, just as abruptly, the opening vanished. For decades, scientists treated the event as an extreme rarity, a combination of conditions so unusual that it might never occur again at full scale. Observations were sparse, direct measurements were almost non-existent, and the phenomenon remained poorly understood, until the winter of 2016. That year, a large opening appeared again in the Weddell Sea, lasting for weeks. In 2017, it returned once more, larger and longer-lived. The hole was back. This is the story of the Maud Rise Polynya, and of how wind, salt, and the deep ocean can temporarily defeat Antarctic winter. To understand why this opening is so counterintuitive, you first have to understand how the Southern Ocean is structured. Most of the time, the ocean is stratified, layered by density. Near the surface sits a layer of cold, relatively fresh water. Below it, hundreds to thousands of feet down, lies a massive reservoir of warmer, saltier water. Because saltier water is denser, it naturally stays below the fresher surface layer. This surface layer acts like a lid. As long as it remains intact, heat from below cannot easily reach the surface, and sea ice can form and persist. Under normal conditions, that lid is strong. But the Weddell Sea is not uniform. Hidden beneath the ice lies a massive underwater mountain known as Maud Rise, a seamount that rises thousands of feet above the surrounding ocean floor, with its summit about 3,300 feet below the surface. This mountain doesn't break the surface, but it profoundly reshapes how the ocean moves above it. The Weddell Sea is dominated by a large, slow, rotating current called the Weddell Gyre. As this circulation flows over Maud Rise, it is disturbed, creating localized turbulence and vertical motion. For years, scientists believed the key mechanism was deep convection. The idea was simple. Under the right conditions, warmer water from depth could rise toward the surface, melting ice from below. Once the surface layer weakened enough, vigorous vertical mixing could take over. Deep convection does happen in the Southern Ocean, but there was a problem. Models showed that, on its own, deep convection was not enough. The fresh surface layer was simply too stable. Something had to weaken the lid before convection could fully develop. That missing ingredient turned out to be the wind. In 2024, a comprehensive study published in Science Advances identified the critical role of wind-driven Ekman transport over Maud Rise. Antarctica experiences some of the strongest and most persistent winds on Earth. When these winds blow across the ocean's surface, they don't just push water forward. Because of Earth's rotation, surface waters are deflected sideways, to the left of the wind direction in the southern hemisphere. This effect, integrated over depth, produces a net sideways transport of surface water. Over Maud Rise, the geometry of the seamount and the structure of the wind field combine to push fresher surface water away from the region. As that fresher water is displaced, saltier water from below moves upward to replace it. The result is subtle but powerful. The freshwater lid thins. Once that lid weakens, another process takes over. And this is where the system becomes self-reinforcing. As sea ice begins to form around the edges of the opening, it undergoes a process called brine rejection. When seawater freezes, salt is expelled from the forming ice and released into the surrounding water. That salt increases the density of the water beneath the ice, making it heavier. This dense, salty water sinks, forming narrow, downward plumes. And as it sinks, it pulls warmer water up from below to take its place. This creates a feedback loop. The more ice tries to form at the edges, the more salt is rejected. The more salt is rejected, the stronger the downward sinking. The stronger the sinking, the more warm water is drawn upward. Heat continues to reach the surface, preventing the opening from freezing shut. The Maud Rise Polynya becomes a temporary vertical conduit, a place where the deep ocean directly communicates with the atmosphere. Through this opening, heat escapes rapidly. Gas exchange accelerates. Carbon dioxide can move between ocean and air, depending on local conditions. Just as importantly, the dense water formed here sinks and spreads into the deep ocean. This matters because the deep ocean cannot ventilate itself. Water masses formed near Antarctica sink to the ocean floor and begin journeys that take hundreds to thousands of years, flowing north beneath the Atlantic and beyond. Along the way, they transport oxygen, redistribute heat, and help regulate Earth's long-term climate. Polynyas like the one at Maud Rise are not the only way this process occurs, but they are among the most intense and efficient pathways when they do appear. Which brings us to the unsettling part. Climate change is altering both the wind patterns around Antarctica and the salinity of surface waters through increased glacial melt. That means these openings could become more frequent, or they could shut down entirely. If they occur more often, they may release stored ocean heat into the atmosphere faster than many climate models currently assume. If they disappear, parts of the deep ocean could become less ventilated over time. Either outcome carries consequences. For decades, a massive opening formed and vanished in the most remote ocean on Earth, largely unnoticed. It wasn't a mystery because it violated physics. It was a mystery because the system was subtle, layered, and hidden beneath ice. Now we know the truth. The ice is not just a passive victim of warming. It is part of an active engine. Wind, salt, seafloor topography, and rotation work together in a delicate, high-stakes balance. The Maud Rise Polynya is not a hole that shouldn't exist. It is a reminder that Earth's most powerful mechanisms often operate quietly, until the moment they don't. The ghost was never supernatural. It was the ocean, breathing, just long enough for us to notice. Veil Origins. Impossible Truths.